Hi everybody. I want to talk to you about a little problem called the conical pendulum. You might know what a pendulum is. It's like a little mass attached to a string that swings back and forth regularly at some rate. Well, a conical pendulum is similar. It's a ball attached to a string, but instead of swinging back and forth, you give it a little push so that it actually travels in a little cone-shaped circle. So it travels forward, swings around, travels back, and traces out a little circle. And what's interesting about the conical pendulum is that even though you have a ball attached to a string, let's say the string has a length L, and it makes an angle theta as it sweeps out this cone, the length of the string is not the radius of the circle. And we'll see why in a second. I love this because it's really like, here's a really fun real life example of it. If you've ever swung someone around in a circle by holding their hands, you notice that they sort of fan out and make a little angle and trace out a little circle with their feet while they maintain a steady height and a steady angle. And that's exactly what the conical pendulum is. So with a conical pendulum, or with any circular motion problem when you're starting, the first thing you have to do before you do anything else is find the circle. Sometimes it's super obvious what the circle is, like for a Ferris wheel, for example, you can see the circle right away. But here, you have to recognize that the circle actually exists in this horizontal plane that the mass is tracing out as it goes around. Once you've found the circle, then you can identify the radius of the circle, which we know is going to be a super important quantity. And then you can see, in this case, how that's related to the length of the string. So we know the length of the string times the sine of that angle that the pendulum is making is going to give us the radius because of this little triangle here. So let's say that theta is given at 30 degrees and L is given at 0.5 meters. That gives us enough to figure out the radius. So 0.5 meters times sine of theta, and we get that the R is 0.25 meters. Now our task here is to figure out how much time it's going to take the pendulum to make one complete loop. So what's the period T of this pendulum's orbit? Now don't confuse that with tension. That's the symbol we're using for period, which is the time to make one orbit. We know it's going in a circle, so we know we're going to need our principles of circular motion. We found the circle, we've gotten an expression for the radius, so now we can get started. Let's come over here and write our equations for circular motion, which is Newton's laws, the circular edition, that the net centripetal force is equal to the mass times the centripetal acceleration, which is given by v squared over r. Now, right now I don't know the mass, and it turns out we're not going to need it. We do know the radius, but we don't know the velocity, and we don't know what the sigma f is just yet. We can't do the sigma f without a force diagram. Before we do that, though, I want to think about a strategy. Where is the period embedded? Where is it hidden in this problem? The forces do not depend on time. The radius doesn't depend on time. The mass doesn't depend on time. But that velocity, we know that when we calculate velocity, we can come over and say that the velocity is equal to the circumference divided by the period. And so strategically, if we figure out the velocity, we'll easily be able to get the period. So that's our secondary goal, is finding the velocity. In order to do that, we're going to need to find the net centripetal force and do a few other tricks. To find the force, we're going to need a force diagram. So let's come back over to our picture and let's draw the components of the tension. And I think I'll draw them in blue so they stand out. So here's our tension. I'm going to call it Ft so I don't confuse it with period. And then we also know that we have weight acting down. Now the weight clearly does not point in the centripetal direction, which is horizontally, but the tension kind of does. And so we're going to need to resolve that into a component that points in the x direction, Ftx, and a component that points in the y direction, which I'll call Fty. Now, of those two forces, now you have to ask yourself which one is centripetal. And of all three of those forces, if we look at the components as independent forces, the only one that's centripetal is the horizontal component of the force. So let's come back over to our sigma F equals ma, and let's put that in. Ftx is providing the centripetal force, and that's equal to mv squared over r, and I'm stuck. I don't know v, I don't know m, I don't know f, I just know r, so there's really nothing I can do further with this equation. On problems like this, you ask yourself, what else do I know? Remember, the ball is not moving up or down. It's in perfect equilibrium vertically. In order for that to be the case, it must mean that the vertical forces are balanced. What's cool about this problem is that even though we're focusing here ultimately on the centripetal forces, it doesn't mean that we still can't apply good old-fashioned Newton's laws when it's appropriate and they can help us. So I'm going to come over here and note that this object is in vertical equilibrium. The net vertical forces are 0. What that means is that Ft in the y direction has to balance out the weight. And that still doesn't help me because I don't know m and I don't know Fty. But it kind of does. And here's a really cool trick that you will see in a couple of different situations. Let's take a look at the tension. I don't like that color. I'm going to make it yellow. Let's take a look at the tension triangle over here. Note that this angle up here is still the angle theta. And in fact, we can relate Fty to Ftx using that angle. In fact, using the tangent function. So we can note that tangent of theta is going to be Ftx over Fty, opposite over adjacent. And if I plug in for Ftx as mv squared over r divided by Fty, which is mg, I'll see the masses cancel out, and I wind up with the equation tan theta equals v squared over rg. Or, if I solve that for v equals the square root of rg tan theta. If I come along now and plug in my numbers, I see that my velocity, if I put in for r and g and tan of theta, I get that my velocity is 1.2 meters per second. And now I'm just one step away from finding the period. Remember, the velocity, which is 1.2 meters per second, is just the circumference, 2 pi r, divided by the period. And so my period is going to be 2 pi r divided by v is going to be my t if I do my algebra, and I get that my period is 1.3 seconds. That's it. So this pendulum will take 1.3 seconds to make one full swing. Hopefully that's helpful. You can see a little bit more of a complicated problem. Let's just recap real quick. First, we found the circle. So find the circle if it's not obvious. Do sigma f in the centripetal direction is mv squared over r. You may need to do components and things like that in order to identify those centripetal forces. And then you might actually need to do other things like sigma fy equals 0 or sigma f. You might need to use Newton's laws in other directions if there's an equilibrium, and that will help you. Once you've done that, though, then you should have all the information you need to solve it. All right, have a good night. See you later.